For the coefficient of thermal expansion, as mentioned, we derived it from the density data that we just looked at using the equation shown here on the right. The coefficient is calculated from a pair of density measurements at two different temperatures. And the basic principle here is that if you know how much a fluid's density changes between two temperatures, you can figure out how much it's thermally expanding. Now, rather than selecting one temperature pair, say 25 and 70 degrees C, and calculating a single value from that, we computed the coefficient for every possible pairwise combination of our 6 temperatures, and that gives us 15 pairwise calculations per sample, which is just more statistically robust. We then applied a Tukey interquartile range filter to those values before taking the mean as a standard outlier detection method, and in this case, there were no outliers identified. And in terms of the results here, we can see that the optical PE sample showed the highest coefficient of thermal expansion, and optical CM had the lowest coefficient of thermal expansion. And physically, what the coefficient of thermal expansion is capturing relevant to the freedom of merit calculations is that a fluid which expands more when heated will generate a stronger density gradient near those hot components. And that's what's going to drive any buoyancy-driven circulation in any natural convection systems.